In our previous video, we showed an example on how to work with circuits containing OpAmps. That circuit is shown here again, and what we got is that if we apply a 1 volt input voltage, the output will deliver a voltage of 9 volts, or about 9 times increase in voltage. Further, we also computed for the potential of V sub 1, and what we got is a voltage of 1 volt. Uh, the potential of V sub 2 is the same as the input voltage, which is 1 volt. Further, we can compute for the currents I sub 1 and I sub 2. So I sub 1 is the current uh, entering the inverting terminal, while I sub 2 is the current entering the non-inverting terminal. So doing that, what we will get is I sub 2 is very close to 0. So I sub 2 is computed as the input voltage Vs minus V1 divided by the input resistance R sub I. So take note that we have an input resistance here, R sub I, connecting the inverting and non-inverting terminals. So that will yield an answer that is very close to 0. Also, we notice that I sub 1 is the negative of I sub 2, so that makes I sub 1 close to 0 as well. So what we have here is that the potential V sub 1 and V sub 2 are roughly the same or are equal, and I sub 1 and I sub 2 are both 0. And this is the property of OpAmps. The OpAmp makes the potential voltages of the uh, inverting and non-inverting terminal almost the same, while making the currents entering those terminals equals to 0. So that brings us to the ideal op-amp, which states that the current that enters the inverting and non-inverting terminals is 0, and the potential voltages of the inverting and non-inverting terminals are equal. So that means that the voltage V sub D is actually equals to 0. Furthermore, ideal op-amp means that the open loop gain is equals to infinite. The input resistance R sub I is also infinite, while the output resistance R naught is equals to 0. This simplification of the characteristic of op-amps makes the analysis of circuits involving op-amps very short. And moving forward, we'll be dealing with circuits containing op-amps as if they are ideal elements. Let's redo the previous problem and assume that our op-amp is an ideal op-amp. So again, if this op-amp is ideal, that means that the currents entering the input terminals are both 0, and V sub 1 and V sub 2 are both equal. So if V sub 1 is equals to V sub 2, and since V sub 2 is tied directly to V sub S, that means V sub 1 must be equal to V sub S. So this must be equals to V sub S. So this is the solution So we can write KCL at this node and at this node. For this node, the KCL is given by this one. So current entering, which is this one, this is the current entering. So it is equals to V naught minus V1 divided by the resistance. And that equals the current leaving, which is V sub 1 minus 0 divided by this resistance. Again, for the ideal op amp, we have this relationship. So using or replacing V sub 1 with V sub S, that will give us the closed loop gain as equals to 9 and V naught equals to 9 volts. So it's almost the same as the answer that we got using the op amp, using the equivalent circuit for the op amp. We now go to some basic configuration of op amps. Here we have what is called an inverting amplifier, uh, where the input voltage is connected to the inverting terminal through some resistance. It is called inverting because the output will be the inverse or the negative of the input, aside from being an amplified version of the input. This configuration uses negative feedback because the output is connected to the inverting terminal via some resistance R sub F. Take note that the non-inverting terminal is tied to the ground. So since this is an ideal op amp, that means that V sub 1 must be equals to 0 volts. So for an inverting amplifier with this configuration, if we compute for the output voltage, that would give us this answer. So for the closed loop gain, that would mean that that would give us a negative closed loop gain equals to this ratio. So as seen, the output is a negative uh, compared to the input with an amplification equals to this ratio. Okay. So how was this derived? Well, what we can do is write KCL here. So current entering is I sub 1. That must be equals to current leaving, which is I sub 2 plus 0, because this one is a 0. I sub 1 can be written as V sub I minus V1 divided by R1, while I2 can be written as V1 minus V naught divided by R sub F. But V1 is equals to V sub 2, which is tied to the ground. So that means this is a 0. Okay. And getting V naught should give us this answer. Let's have an example. So here we have an ideal op amp, and we are required to compute for the current through this feedback resistance. So let's call this I sub F. So to compute for that, first this is an ideal op amp, so therefore this is since this is 0 volts, this node here must also be 0 volts. This is 0 amps. Okay, this is 0 amps. Well, here is not, this is not 0, so let's call this input current I sub I. So we can conduct a KCL there. So let's say this is point P. So KCL at point P. So current entering is I sub I must be equals to current leaving, which is I sub F plus a 0. I sub I can be written as 45 millivolts minus a 0 divided by 4 kilo ohms. Okay, and that should be equals to a 0 minus V naught divided by 280 kilo ohms. And that should give us V naught equals to negative 3.15 volts. Okay, now to get IF, we go back to this expression. So this is actually I sub F. So that would be negative negative 3.15 divided by 280. Okay, so that would give us 11.25 microamperes. Okay, so this is the answer here. Another basic op-amp configuration is what we call the non-inverting amplifier. So here we have the input voltage as tied directly to the non-inverting terminal. So that means that this terminal here, V sub 1, must also be equals to this must be equals to V sub I. So the non or the inverting terminal is tied to the ground through the resistance R sub 1. So computing for the output voltage, that would give us this answer. So how do we get this? So we can write KCL here. So current entering I sub 1 must be equals to current leaving I sub 2. I sub 1 is 0 minus V sub 1. But V sub 1 is V sub I. So divided by R sub 1. And I sub 2 is V sub 1, which is V sub I minus V naught divided by R sub F. So solving for V sub naught, that should give us this answer. A special case for non-inverting amplifier is what we call the voltage follower configuration. So if we let R sub F equals to 0, that is a short circuit, and R sub 1 equals infinity, so that means an open circuit, what we get is a voltage follower. So here since our output was derived to be like this, and this is 0, while this is an infinity, this makes this ratio equals to 0. So that means our output is also the input. Okay. So you may wonder why not just connect the input to the output directly, since this configuration simply copies the input. Well, this kind of configuration has advantages, and one of that is the input impedance is very high. So that means the input is completely isolated from the output. So there is some form of protection for the input. Let's have another example. So here we are asked to find the output. Now this circuit um, doesn't seem to look like the configurations, the basic configurations that we have discussed previously. Although we could probably say that this is a non-inverting amplifier because the input is connected to the non-inverting terminal via the or 4 kilo ohm resistance. So what we can do is um, simplify the circuit first. So here is our circuit again. So maybe what we can do is convert this first into its Thevenin's equivalent. So that means that we're looking for a circuit that looks like this. We can compute for VTH using voltage divider. So this is 8 kilo ohms, 8 plus 4 kilo ohms, and that should give us 2 volts. For RTH, after shorting out the input voltage, that should give us 4 parallel with 8, and this should give us 8 thirds ohms. Since this is an ideal op amp, that means the current here is 0, as well as here. So that makes this point equals to 2 volts. And also this one has 2 volts. We can write KCL here. So current entering. So let's say this is the current direction here. Here, this is the current direction. No current entering. So that means 0. There's no current. There's no current entering. Only current leaving. So this current can be written as 2 minus 0 divided by 2K. This current can be written as 2 minus V naught divided by 5K, and solving for V naught, that should give us 7 volts. Okay. As mentioned before, one of the functions of the op amp is to sum up signals. So here we have a summing amplifier where the op amp adds 3 signals, so V1, V2, V3. The signals are connected to the inverting terminal via their resistances R1, R2, and R3. We can compute for the output voltage by conducting or writing a KCL on this node. So there we have I sub 1 plus I sub 2 plus I sub 3 equals I. Okay, but I sub 1 can be written as, so take note, since this is 0 volts, this point here is also 0 volts. So therefore, I sub 1 can be written as V sub 1 minus 0 divided by R1. Uh, I2 can be written as V2 minus 0 divided by R2. V3 is V3, or I3 is V3 over R3. And I is 0 minus V naught, or negative V naught over RF. And solving for this one, that should give us this one. So let's have an example using the summing amplifier. So here we have three voltages, uh, all connected to the inverting terminal via their series resistances. So to find V naught, we can use the formula that was shown earlier, since the configuration is exactly the same as that circuit that was given earlier. So let's do that. Uh, so V naught is equals to the negative. So RF is 8 divided by 20 times 1.5 plus 8 over 10 times 2 volts. So this times plus 8 over 6 times 1.2 volts. And that should give us negative 3.8 volts. Take note that the output is not really the sum of the input signals, although we could make it an exact sum by letting the series resistances equals to R sub F. Also, the output is a negative, meaning it has some inverting function uh, that happens to that computation. So this is the answer. Now to get I naught, what we can do is we can perform KCL here. So for example, the current here is in this direction, while here is in that direction. So that means I naught is the sum of these two currents. So this current and this current. The current on the top is V naught minus this voltage here, which is a 0. So that is 0 divided by 8K plus this voltage here, V naught minus 0 divided by 4K. And that should give us negative 1.425 milliamps. Okay. Uh, so let me summarize the answers. Aside from V naught and I naught, have I have shown here the sum of the currents voltages. So for example, this one is 1.5 minus 0 divided by 20K This one is 2 divided by 10K, while this one is 1.2 divided by 6K. This current here is equals to the sum of these three currents, okay? While this current here is V naught minus 0 divided by 8K. V's current here is equals to V naught divided by 4K. Okay,